1, 0.
1, 2, 3, 4.
Hi everyone, today we're going to look at the remainder theorem and the factor theorem. So this is a big one for pre-calc 12. It's a big extension in terms of everything we've done with long division and synthetic division from last class. So for the remainder theorem, it's simply stated right here, and it's not going to make a lot of sense when we read it for the very first time. When a polynomial p of x is divided by binomial x minus a, the remainder is p of a. So it's a very theoretical looking definition of the remainder theorem. So let's look at something a little bit more practical. I'm going to look back to an example from last class, and I'm going to take example 3. And you could scroll back to example 3 if you want, but if not, then just trust me that if we have something where we take a look at our division statement, so we know that the dividend is going to be equal to the divisor times by the quotient plus the remainder. Okay, and we looked at that last class. So let's give an example of a statement like that. So if we recall back to example 3, we had a dividend that said 2x to the 4 minus 5x cubed plus x minus 4. And that's going to be equal to the divisor of x minus 2. Our quotient turned out to be 2x cubed minus x squared minus 2x minus 3, and then the remainder was subtract 10, negative 10. Okay, so if you were to expand the right side, it would equal the left side right there. And what our remainder theorem is saying is this. Pay special close attention to the divisor. And if the divisor is x minus 2, and you would put in a positive 2 for x, you substitute in positive 2 for x right there, then that's always going to make this say 0. And it's going to be multiplied by your quotient, and 0 times your quotient is going to stay 0, meaning you're going to be left with nothing but this back term right here. So that means when you have something in the form of x minus a, when you substitute in an a for x, that's going to create something in which everything's going to equal 0 except for this back thing here, which will be your remainder, and that will tell you your remainder almost instantly. So imagine you look at this statement right here. If we put in 2 for x, it's going to tell us that we're stuck with this negative 10. So what that does is that allows us to be able to answer the remainder very quickly for questions. And you'll see that you're going to start to face some questions in which now it says, don't worry about telling me what the quotient is. I only want to know what the remainder is. So look at example 1, and it actually even says, without dividing, what's the remainder when this is divided by x minus 2? So what we can do is we can take 2 and we can sub it in. And if we do something like that, then pretty quickly we could say, okay, 2 to the power 4 is 16 times 2, 32, minus 24 plus 4 minus 3. So we would get 8, 12, 12 minus 3 is 9. Okay, so as crazy as this is, you can now just say your remainder for this equation, if you were to simplify everything, would be 9. Now we could easily check this by doing synthetic division, and in fact for this first example, let's do that just to make sure, and this is a good refresher to see if we remember everything we learned from last class with synthetic division. So we have a 2, negative 3, we have no x squared, so we represent that by putting in a 0. And then when we take a look at this, we could say, okay, 2, that gives me 4, 1, 2, 2, 4, 6, 12, add that, negative 9. My remainder is, sorry, positive 9. Negative 3 plus 12 we get positive 9 right there, we had positive 9 right there, and it's all good. Something like example 2 is a common question because now you have something where it's well beyond anything in x to the power of 4 and x to the power of 5 even. We have x to the power of 17. So there's no way that you would even try synthetic division for something like this because you'd be writing out 18 coefficients for your divisor, for your dividend, just to be able to have a chance to be able to solve that. So for here, what we can say is this. If it's being divided by x plus 1, we can just say we can have negative 1 substituted in for our x's, and we would get something that we can answer quite quickly. So here we get negative 1 to the 17 is an odd number of negatives, so we're going to have negative 1. Then we're going to say minus 2 plus 7, and then we would get negative 3 plus 7, so we would get positive 4. So we get a remainder of positive 4. Our very last example from the previous lesson had a question where you had to solve for a k value. So now we can actually solve for these k value questions a second way, and I think I alluded to that in the previous class. So if we were dividing by x minus 2 using the remainder theorem, we could now say that we can substitute in 2 for wherever we have an x right here. So we could say we have 2 cubed minus 2 times 2 squared plus 2 plus k, and that's going to give me the remainder. And in this case, we know what the remainder is. We know it's 5, and they're saying what value of k would make this statement true. So we're going to have to do a little bit of algebra to be able to solve for k. So you could say 8 minus 8 plus 2 plus k equals 5. The 8's cancel each other out. Subtract 2, and k will be 3. Okay, so an extension to the remainder theorem is something called the factor theorem. And the factor theorem is the remainder theorem, but it just tells us one additional piece of information. It says that when you have a perfect factor, you're going to be left with a remainder of 0. If you want to look at this with just pure numbers, you could say something like, well, if 54 divided by 9 goes in a perfect 6 times, the remainder is 0. Therefore, 9 is a factor by definition. But 54 divided by 5, well, that goes in 10 times. You'd have a remainder of 4. So therefore, 5 is not a factor. So when you create something that has a remainder of 0, then we know that it was a factor. Okay, let's try 2 examples right here. And all we're going to do is we're going to test the remainder theorem. If we get 0, it's a factor. If we don't get 0, it's not a factor. Okay, so we substituted in 1, and we're just going to see what we come up with this. So we would get 3 plus 4 minus 3 minus 3 minus 10. Okay, so let's see what we get here. If we did something like that, we would end up with 7 minus 3, which would give us 4. 4 minus 3 would give us 1. 1 minus 10 would give us negative 9. So that is not 0. So then we can say that is not a factor. Okay, here we sub in 2, and we would say 2 cubed minus 2 times 2 squared plus 3 times 2 minus 6. And we would get 8 minus 8 plus 6 minus 6. Those are going to each cancel each other out. We get 0. And so then that is saying that x minus 2 is a factor. Okay. We got a few new terms today. Our final new term for today is something called the rational root theorem, and that's just allowing us a way to be able to find out what are the possible factors. This part here is going to lead into being able to put everything all together from what we've done from the past couple classes, and I think it's one of the more interesting things that we learned in pre-calc 12. Let's take a look at the first example and use that to be able to explain the rational root theorem. So the question is saying, algebraically find the zeros of y equals x cubed minus 9x squared plus 20x minus 12. So the first thing that you should think about is you should say, well, when I'm going to try to factor this and figure out what all of the solutions are for that, I've never really had to do a question that's bigger than a trinomial in terms of being able to factor it. I know in some pre-calc 11 questions and a couple pre-calc 12 questions, you'll see 4 terms like we have right here, and you would do something where you would factor by grouping, but that's a pretty specific case too. So right here, we have something where we have more than a trinomial, and they're going to ask us to factor and solve it. And I find that very, very interesting because we haven't had to do that ever before. So what could we do? The first thing is they say, let's list all of the possible factors. And the rational root theorem is going to tell us that the possible factors, the possible rational factors, can be derived by looking at the factors of the constant, this back term, this negative 12 right here. There's going to be one exception to that if there's a leading coefficient, but in this case we don't have a leading coefficient, so we're all good. And so I'll just write rational root theorem right here. And what I'm going to say is we're going to say that our possible factors are plus or minus, because it could be a combination of them, but it'd be some plus or minus of 1s, 2s, 3s, 4s, 6s, and 12s. And that's because those are things that possibly times to equal negative 12. So plus or minus 1, 2, 3, 4, 6, 12. Now, based off of that, there's a chance that some, or a few of them even, are going to be possible factors for this question. And what we need to do now is we need to test them, and we need to see what we could do to see what creates a factor. And this part here is something it's a little bit tricky now. So you have to pick one of these numbers and you have to sub it into the equation that we have, and based off of that we have to find out something that's going to produce a remainder of 0. We're applying the factor theorem right here. So if we're going to get a remainder of 0, it's pretty hard to eyeball a number to sub in that's going to give you 0. So the tip I would say is pick small numbers. Okay, so we want to pick small numbers, and if there's something that you can see, go for it. So the number that I'm going to try to start off with this first one is 1, and 1's the number I try almost every time just to begin with. And it could be frustrating if it doesn't work for the first few times where you don't get a remainder of 0, but let's pick 1 and let's see what happens. So step 2 is going to say, let's sub in 1 and let's apply the factor theorem. So we're going to say we have 1 cubed minus 9 times 1 squared plus 20 times 1 minus 12. And if we do that, we get 1 minus 9 plus 20 minus 12, and that's going to give us 0. And this is something we need 0 to be a factor. So this is a good thing. That means that 1 is a factor, which means that x minus 1 would be one of our overall factors. So let's write that. Therefore, x minus 1 is a factor. Because it's an x cubed, we have a cubic function right here. We know that there's upwards of 3 answers, and we don't know what the other 2 answers are. So one possibility is you could continue to substitute in numbers like we just did here and try to find out what else would equal 0. But what we're going to do is we're now going to use the knowledge that we know that 1 is a factor, and we're going to use that to be able to use synthetic division to be able to find the remaining factors. So if we say 1 and then we draw our synthetic division right here, and we would say we have 1, -9, 20, -12. So if we have something like that and we want to figure out what this looks like, we could say bring down the 1 times it, -8, -8, 12, and phew, we get a remainder of 0. We knew that because we knew that 1 was a factor, so we have to have 0. That has to say 0. But it leaves us with a trinomial, and that trinomial is x squared minus 8x plus 12, and that is going to pair with the x minus 1 that we had already seen from before, and those are going to produce us our remaining factors. So if you take what we have right here and you say x squared minus 8x plus 12 and you factor that how you would traditionally factor a trinomial, you can now say we would get y equals x minus 1, x minus 2, x minus 6. And that would produce, they want us to find the zeros, so that would produce zeros of 1, 2, and 6. So it's interesting to note right here that we chose 1 to begin with in our test of the factor theorem. But if we had picked 2, positive 2 is one of the rational root theorem numbers to be able to test, or we picked positive 6, we still would have had a chance to be able to do the same process and come up with the exact same solution. So these are our 3 solutions. And the final thing that I would say to this example is you can go back and you can check it, and you can check it by putting that in your graphing calculator. So if you were to graph what we have right there, you would plot that in for y1 and you would look at the zeros, and your zeros would be 1 and 2 and 6. So as you're going about these for the first times, I actually highly recommend using your graphing calculator to be able to see what that looks like. Okay, example 7. Algebraically find the zeros of something like this now, where we have a leading coefficient. So we have a leading coefficient that is not 1. So when we apply the rational root theorem, we're still going to have factors of plus or minus 1, 2, 3, and 6. Okay, those are all the possible factors of that back constant value. But we're also going to have the factors of what we created divided by the factors of the leading coefficient. And the leading coefficient has factors of 1, 2, and 4. Now, because dividing by 1 doesn't change anything, we can ignore that. But it means that we now have to also take the factors that we found right here and divide them by 2 and divide them by 4. Okay, you might need to pause that, rewind that, and listen to that again. But that's going to create something that's going to look like this. So I'm going to do it a little bit overkill right now just to begin with, where I'm going to list absolutely everything. And then after that, we'll be able to see why we could have maybe done this a little bit faster. So those are all of the possible factors using the rational root theorem. Those are all the possible rational roots that could exist for this question. Now, given something like this, we realized we didn't need to list 2 over 2, and we didn't need to list 6 over 2, because 2 over 2 is 1, we've already stated that, and 6 over 2 is 3, we've already stated that. We've already stated 1/2 right there, and we've already stated the 3 over 2. So we actually aren't adding a whole lot to it. We're adding just the terms that are now left over there. So based off of this, we have to pick one of these numbers, we have to test it out, and then we have to see, well, would which one would work for something like this. So again, this could be a frustrating process. You might be able to eyeball it, look at it, and say, you know, if I sub in 1 for something like this, I just know that that won't work. I know that I can do that in my head pretty quickly, and that's not going to be able to balance out. So let's try something else. So what if we said, let's try subbing in -2, and you might say, well, why are we trying -2? And that's because I'm feeling pretty good that -2 is going to work here, and that's going to save us a couple minutes. But if you had picked another number like -1 or +2, those are good numbers to test out as well. So we take 4, we times it by -2. Okay, and let's see what happens here. We get, oh, sorry, I forgot to put these guys up here. Okay, so we get -8 times 4, we get -32. 4 times 12, we get 48, minus 10 minus 6, and that is going to give us 0. So -2 is a factor. -2 is going to work for us. Now, if you're still in that, if you're still saying, well, like, how did you know it was going to be -2? If you're allowed a graphing calculator, or when you're doing your homework, you want to be able to have your graphing calculator on hand, you could always enter in the original into y1. You could find the zeros, and you would see that -2 is a clear 0. It's clearly one of the solutions, and all we're going to do right now is just show the algebra behind that. So it might save you a little bit of time if you're feeling that you want to be able to go back and forth between your graphing calculator and showing the algebra. So we take -2 here, and let's do our synthetic division with 4, 12, 5, and -6. So we know we want to get a remainder of 0 when we do this. And luckily we do. Okay, yes, that works. And we're left with something that's going to say 4x squared plus 4x minus 3. Okay, so if we're saying solve this, we now have a trinomial, and then we're going to have to factor that 4x squared plus 4x minus 3 to pair up with the x plus 2. And if we do that, let's see what we get. Okay, and this could be -1 plus 3. Let's see if that works. Yes, that looks very good. Okay, so that means that we're going to have solutions of x equals -2, x equals 1/2, and x equals -3/2. Okay, so those are the 3 zeros for that question. So a little bit more now when we have a leading coefficient, but the same sort of process from what we had from that previous example. Okay, we have one more final example. Now we have something here that has an x to the power of 4. Okay, so if we have an x to the power of 4, let's see what's going on. Okay, so the rational root theorem, we don't have a leading coefficient of anything other than 1, so we just know it's going to be all these multiples that would produce something that could times, to 24. Okay, so we have lots of options right there. Okay, so once again, we're going to have to think about what we could potentially put in. Let's try subbing in 2 here, and let's see what happens. Okay, so we get 16 minus 40 plus 8 plus 40 minus 24. This is looking pretty good. 16. We get a remainder of 0. Phew. Okay, so that means that 2 is one of our factors. Okay, so based off of that, let's see what we could say. That means that we could go and we could put in 2, and then we would have 1, -5, 2, 20, -24. Okay, good. We needed that remainder of 0 there. So that means that when x minus 2 is one of our factors, we'd be left with x cubed minus 3x squared minus 4x plus 12. And based off of what we have right there, guess what? We need to try to sub in something again because we're now not left with a clean trinomial that we could factor. We actually have to try this again. Now, someone may look at that and say, you know what? This actually looks like one of those exceptions where we might be able to use factoring by grouping to be able to find the rest of these solutions, and you're correct on that. Because that's such a rare exception, we're going to pretend that we don't know that, and we're going to try to sub in something else to see what we could potentially get. So right here, let's try to sub in, if we're looking for another number that could potentially work, let's try 2 again, and let's see what happens. So if we go 2 cubed minus 3 times 2 squared minus 4 times 2 plus 12. And that is also going to work, meaning that x minus 2 worked the first time and it worked again the second time, so it's going to be a double 0 right there, a minimum of at least a double 0 right there. So when we do that and we take our 2 right here and we use our cubic function that we're left over with, we would have 1 negative 3 minus 4 plus 12. We would now say we have y equals x minus 2 squared, x squared minus x minus 6, which becomes x minus 2 squared, x minus 3, x plus 2. And based off of all of that, we can now say that we have solutions of x equals 2, x equals 3, x equals negative 2, and this x equals 2 actually occurred twice, so we'll list it twice because it has a multiplicity of 2, and those are the 4 solutions for that question. Now, definitely that went quite smoothly given that everything worked out with testing values for the first time. So I just want to show you one more thing. I want to go into the graphing calculator, and I just want to be able to say, here's the 3 functions that we had, and if we're taking a look at something like trying to figure out what we could potentially have for it, let's highlight this most recent example, and let's say we did something where if we graphed this example here, notice that when you take a look at this, you could eyeball it and say almost instantly, hey, negative 2, 2 bounces, so it looks like it hits there twice, and it hits at 3. So we can actually find our zeros almost instantly just by looking at that. And if you're not certain that that's going to be the case, then there's lots of things you could do. You could always say second trace, and let's find the zeros, and then we could work on our whole left bound, right bound concept, and we'd be able to find them out that way. So based off of something like that, whoops, we could say enter, and we get negative 2 as one of our solutions. We could find out that 2 is going to be a solution, and that clearly bounces, and then you can find out 3 is a solution. So I won't go through the remaining parts of that, but that's how you could find out the solutions fairly quickly and use your graphing calculator to your advantage for something like this. So those are all of the examples for today. The homework has some pretty good questions, and they're able to ask some questions that really extend upon this lesson. So I'm sure a lot of you are going to want to come into the tutorial room and be able to ask some more of those questions, but that's all we have for today. Thanks.